Hello again. In this continuation of integration by parts lesson, we're going to continue with 3 more examples. In this case, we're going to focus on what we call repeated integration exercises or integrals, in which we're going to see that when we apply the integration by parts formula, we're still going to be left off with an integral that cannot be solved directly. So we're going to need to use integration by parts again. That's the whole idea of this example. So this would be an example of something like that. Now we have an x squared instead of just an x, so this changes things a little bit. So again, as I said in the previous video, there's 2 ways you can look at this. One way is to use islet. We have an algebraic here and an exponential. Algebraic comes first from left to right, so x squared should be our u, and dv is just the rest. Another way to look at it is to ask yourself, which of the 2 is easier to differentiate and easier to integrate? So in this case, we have an e to the x, which is equally as easy to differentiate or integrate because it's always the same. So that's why I just, it's kind of ambiguous. I just tend to use islet. I always like to compare both methods from the moment I decide I'm going to use integration by parts to solve something, I just decide, hey, am I going to use islet or am I going to use like common sense? Anyway, moving on, du is going to be 2x dx, and v is going to be just e to the x. Remember, you don't need to put a plus c here, it's not necessary at the moment. Let's rewrite the integral. This is going to give me u times v, so x squared e to the x minus the integral of 2 times x e to the x dx. Now we've made some progress because now it looks simpler. However, we do know from our previous video that this needs to be solved using integration by parts, and it would basically be the same thing. We would have to use islet again and pick x to be our u because of the priority. Now, since we've already done this in the previous video, I'm just going to go ahead and give you the answer for this blue portion. So feel free to watch the other video if you want to know more details. So this is a result without the plus c, of course. So I'm just going to distribute the 2, so 2x e to the x minus 2 e to the x plus c. So this is an example. As you can see, the integral we were left off with, once again, is one in which we need to use integration by parts. Now let's look at this other one. So integral of u dv is uv minus integral of v du. We're going to use islet to see if we determine what's best. Now there's an exponential function here and a trig function. Trig comes first. So islet is telling me that u should be sine of x. However, I can say this with experience that it's going to be slightly easier if you just use e to the minus 2x. Now, again, it just comes with practice. In my case, I just had to do this exercise both ways to see which was easier. So this is, I guess, an example of you can solve it both ways. When you pick your u, it's just a matter of a little bit of experience. So we're gonna do it with this. You feel free to do it in reverse order. I'm just gonna do it this way to save some time. So du is gonna be minus 2 e to the minus 2x dx, and v is going to be minus cosine x. So our integral is going to be equal to minus cosine x e to the minus 2x minus the integral of v, which is minus cosine, so this turns into a plus. So cosine x, and then the rest is minus 2 e to the minus 2x dx. Let's quickly rewrite this. So we're going to have minus twice the integral of cosine x e to the minus 2x dx. And we can see, once again, that we have to use integration by parts. Again, because, it's just two different functions, we don't know how to integrate them directly. Now, if you need to do integration by parts again, because it's a repeated integration type of example, then your new u, and I'm going to write that in blue, if you picked an exponential, then stay with the exponential. It's going to make things easier, all right? Don't mix the u's and the dv's. So now my new dv is going to be sine of x instead of cosine. It's going to be cosine instead of sine. Right, so v, it's easy, it's just sine. And du, once again, is minus 2 e to the minus 2x dx. So I'm going to rewrite everything. So at the moment we have minus cosine x e to the minus 2x. That part is already finished. Now we have a minus 2 being multiplied by all of this blue thing. So uv, that's sine x e to the minus 2x, minus the integral of v du, so minus 2 sine x e to the minus 2x dx. So before we move on, I'm going to quickly distribute that 2. Awesome. So you would think that this is like very hard, very long. We still have a long ways to go. But I want you to notice something very interesting. Notice that have you noticed that this integral is exactly the same as the original problem? This is a very cool example of repeated integration. Now, once you get to this point, you're pretty much done. You just have to do a little bit of algebra. You don't need to keep doing the whole integration by parts thing because it's going to be never ending. So the way you solve this is typically what professors do and the book does is we set this integral to be equal to capital I. It's just convention, okay? It could be any letter. Capital I is just a convention. So you can look at this as I equals minus cosine blah 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 minus 4i. Now algebraically you can solve for I, and that's what we want. And I guess a more formal way to do this too is to say just let I equals blah blah blah. You can always write that too. Now I'm going to rewrite this just quickly. So I equals minus cosine blah 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 minus 2 blah 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 minus 4i. Obviously we just move the minus 4 to the other side or add 4i to both sides. Same thing. So this cancels. We're left off with 5i equals blah blah blah. Now I'm going to make some space here just to write the final result. The final result is going to be I, which is equal to the integral of e to the minus 2x sine x dx equals, so we're dividing everything by 5, so minus 1/5 cosine x e to the minus 2x minus 2/5 sine x e to the minus 2x. And don't forget the plus c. And we're done. Cool. So let's look at a final example. Great. So up until now, we've looked at examples where we have two different functions being multiplied, except for the natural log example. This would be another sort of slightly different example because we only have one function. I mean, it's being raised to the third power, but it's really just one function. It's secant. So that means that islet is not going to be useful here. But we're going to use integration by parts. And the way we're going to work on this is we're going to split this secant into two parts. So I'm going to take one of the secants separately. Let me rewrite the equation, the formula. Now, we don't have eyelid here to select, so I'm just going to use my common sense. Which of the two is easier to take a derivative of? Well, from experience, secant is easier. I'm going to pick that. Another way to look at it is, which of the two is easier, and that's how I find my dv, which of the two is easier to integrate? Is secant easier or secant squared? Well, for me, secant squared would be easier because I know that the derivative of tangent is secant squared, so we can use that basic list of derivatives in reverse order, just like I said in the previous video. And integral of secant is just slightly bigger, harder, so it's just better to just pick this arrangement. Okay. Now, as always, I find my du and my v. So du is going to be secant times tangent dx, and v is just going to be tangent. So the integral of secant cubed is going to be uv minus the integral of v du. So secant tangent, I'm going to join those tangents. And this is a repeat integration example because we can't solve that directly yet. So how do we do this? Do we use integration by parts again? Well, this is interesting because this is a case where we don't really have to use it again, at least for now, and I'm going to tell you why. Because I can take, and I'm just going to do it here. I can just take this tangent squared and use the identity that tangent squared is equal to secant squared minus 1. And the way I know that is because I have sine squared of something plus cosine squared of something equals 1. You divide it. If you divide everything by cosine squared, then you get tangent squared equals secant squared minus 1. Okay, so that's how I know this. So it's going to be secant tangent minus secant times secant squared minus 1 dx. What I'm going to do now is just distribute the secant. And now I'm going to be a little bit clever. I'm going to notice that, hey, this portion looks exactly the same as the original exercise if we just take this out. So I'm going to do just that because I can just do it. I can say this is the same as this, right? And now we have two exact replicas. This is going to be I, right? It's going to be I. So I can take that I to the other side, which is going to give me a 2i, and then I can divide everything by 2, and I would have my result. Finally, I just have to integrate secant x, which is already among our list of basic integration table. So this is natural log tangent x plus secant x. And therefore, our final result is going to be I, or just secant cubed x dx, equals 1/2 secant x tangent x plus 1/2 natural log absolute value tangent x plus secant x plus c. And we're done with our examples. Thank you for watching. If you have any questions, feel free to post them in the comments and share this with your friends if you find it helpful. And I'll see you in the next lesson. Bye-bye.